Slide 1. Atoms, Molecules, and Seawater Chemistry, Topic 04A, Part 2, Bonding and Water's Unusual Properties. Slide 2. Surface tension, adhesion, and cohesion. In the last unit, we learned that water molecules have an electrically positive side and an electrically negative side. Thus, one side of the molecule is attracted to positive things, and one side of the molecule is attracted to negative things. This means that water molecules are attracted to nearly everything. Slide 3. Adhesion occurs when atoms or molecules of different substance remain together, stick together. Cohesion occurs when atoms or molecules of a liquid remain together, stick together. Surface tension is the tendency of atoms or molecules of a liquid to remain together, stick together, and resist or prevent other objects from entering the liquid. Slide 4. Water beads up, forms a drop, better than other liquids, because the water molecules are strongly attracted to one another. The water molecules strongly bond with one another, so the water molecules hold together instead of being pulled down and apart by the Earth's gravitational pull and spreading out. In short, water forms a drop. A drop of water is the classic example of cohesion. Slide 5. Water molecules hold together so strongly that small, dense objects, like a paper clip, will float on the surface of the water if you place them on the water gently. We call this effect surface tension. Normally the downward pull of the Earth's gravity is stronger than the upward push of the water below the small object, but if the water molecules at the surface are bonded together, they act like a net to provide extra support. If the object is light enough, the electrical attraction can be enough to keep it afloat. Once the object pierces the surface and thus breaks the bonds between the water molecules, though, the ordinary rules of density apply. Water molecules also bond more strongly with most other substances, adhesion, than other liquids. This is why drops of water remain on the window of your car after it rains or on your body after a shower. The water molecules strongly bond with the glass molecules of the window or the molecules of your skin, allowing the water molecules to resist gravity's downward pull. The strong bonds formed by water molecules increase water's viscosity. Recall that the viscosity of a fluid relates to how easily the fluid flows and thus the amount of friction that objects feel as they move through the water. For many plankton in the ocean, the bonds that neighboring water molecules form with their bodies are so strong that the plankton do not sink or sink much slower. The strong bonds of water molecules make it harder to swim, to push through the water. Imagine trying to swim in honey. This is something like what tiny plankton feel like when trying to swim through water. Slide 6. Water is often called the universal solvent. This refers to water's ability to break down most other substances. For example, soaking dirty dishes in water makes them easier to wash. The dried food on the dishes is strongly bonded to the dishes, but water molecules' strong electrical attraction pulls on the molecules of dried food. Water molecules try to bond with the food molecules, pulling them off the plate or at least weakening the bonds between the food molecules and the plate's molecules enough for you to more easily rub the food off. Slide 7. Recall that the water's hydrogen bonds are weaker than the bonds that hold most solids together, like the ionic bonds of salt crystals. If water molecules form weaker bonds than salt atoms, how can water dissolve salt? How can it make the atoms in a salt crystal break apart, to separate from one another? A single water molecule is not attractive enough, but a group of water molecules, all pulling together, is strong enough to overcome the electrical attraction holding the atoms in salt together. The bonds between the atoms or molecules of solids are quite strong, so many water molecules all pulling together are needed to separate them. It is something like the game tug of war between adults on one side and a group of children on the other side. The adults represent the salt atoms, they pull strongly, they have strong bonds, so they stay firmly together and create a solid object. The children represent the water molecules, they are weaker than the adults. If two adults pull against two children, the adults will win. However, if enough children are on their side of the rope, they will defeat the two adults. In short, a big group of smaller, weaker people can overwhelm larger, stronger opponents if they work together. Slide 8. Water is a good solvent, better at breaking down most substances than other liquids, because water forms stronger bonds. In the tug-of-war example, water molecules are like fourth graders and other liquids are like first graders. The fourth graders are bigger and stronger than the first graders, so it takes fewer of them to win against the two adults on the other side of the rope. This means other fourth graders can go off and defeat other adults. Similarly, fewer water molecules are needed to surround and bond with each salt atom, so other water molecules are free to go off and dissolve more salt. Slide 9. Note that when water dissolves salt, the salt atoms are not destroyed. The sodium and chlorine atoms are just separated from one another, they move apart. Thus, dissolving does not necessarily destroy the substance that gets dissolved. The substance may just end up moving around as individual atoms or molecules in the liquid. This idea will be important to bear in mind later when we discuss pollution. When water breaks down substances like pollutants, it may separate the atoms of the pollutant molecules, destroying the pollutant molecules, or it may separate the pollutant molecules and carry them around, spreading the pollutants around within the liquid. Slide 10. Water can only dissolve so much salt, it can only hold so much salt. Eventually the water will become saturated and unable to dissolve any more salt. Water is saturated and unable to dissolve more salt when all the water molecules in the water are bonded to salt atoms. Water molecules that are bonded to salt atoms are stuck to their own salt atoms. The already bonded water molecules are unavailable to bond with and break apart any more salt crystals that are added to the water. The dense salt crystals will simply sink and pile up on the bottom of the container. You can think of water molecules that are bonded to salt atoms as being married to their salt atom that they are bonded. Thus, they are not looking for other partners to bond with. That would just be wrong. In saturated water, all of the water molecules are taken, so newly added salt atoms cannot find any unattached water molecules to bond with. It is like being single at a party filled with couples. Slide 11. Calculating salinity. About 3.5% of seawater is salt, the other 96.5% is water. Salt refers to all of the substances dissolved in ocean water, which include gases like oxygen and nutrients like phosphate, not just the components of ordinary table salt, sodium, and chlorine. Oceanographers typically describe salinity in terms of parts per thousandth or ppt, not percentages, so oceanographers would say that the ocean has an average salinity of 35 parts per thousandth. Why do oceanographers do this? Scientists use the metric system. Mathematically, the metric system is a lot easier, and doing science is hard enough without making the math harder than it needs to be. If scientists report their measurements in parts per thousandth, then they can quickly determine how much salt is in the water. 1 part per thousandth is about 1 gram of salt per liter of seawater. A liter is half of a large bottle of soda. A gallon is a little less than 4 liters. So, if the ocean's salinity is typically about 35 parts per thousandth, then there is about 35 grams of salt in each liter of seawater. It is very easy to convert from percentages, which are parts per hundredth, to parts per thousandth. Just move the decimal point to the right by one place. So, 2.0% is 20 parts per thousandth, 3.1% is 31 parts per thousandth, 4.7% is 47 parts per thousandth, and so on. This works because 2 out of 100, 2 divided by 100 equals 0.02, is the same as 20 out of 1000, 20 divided by 1000 equals 0.02. If you multiply both the top and bottom, the numerator and denominator, by 10, then you are not actually changing the number, you are just changing the fraction from out of 100 to out of 1000. Water is rarely pure. For example, good-tasting tap water has a salinity below 0.6 parts per thousandth, and premium bottled waters have salinities below 0.3 parts per thousandth. In coastal areas which get lots of fresh rainwater runoff from the land, ocean salinity may be as low as 10 parts per thousandth. We call such water brackish. In places with little rainfall and lots of evaporation, the seawater salinity can be over 40 parts per thousandth, and we say the water hypersaline. The words brine or briny are also used to describe salty water. The word haline also refers to the saltiness of water. More haline water is more salt, and less haline water has less salt. To calculate the salinity of a solution, just divide the amount of salt by the total amount of salt water that is made. For example, suppose that we mixed 2.5 grams of salt with 100 grams of water. The total amount of salt water would be 102.5 grams. So, 2.5 grams of salt divided by 102.5 grams of salt water equals 0.0243. To make this into a percentage, we need to multiply by 100, so we get a salinity of 2.43%. To make this into parts per thousandth, we need to multiply by 1000 instead of 100, so we get a salinity of 24.3 parts per thousandth. To make it easier to measure ocean salinity, in 1978 oceanographers changed from using parts per thousandth to practical salinity units, PSU. 1 PSU is about 1 parts per thousandth, so I am not going to worry about the difference, and will use parts per thousandth. The change was made because oceanographers typically determine seawater's salinity by measuring its conductivity. Salts are electrically charged atoms, ions, so they conduct electricity. PSU is determined by comparing the conductivity of a sample of seawater to the conductivity of a specially made salty solution. Slide 12. pH, acids and bases. When a substance that we call an acid enters ocean water, its molecules often split, giving off hydrogen nuclei, H+, single protons. The water then becomes acidic. The wandering acid H+ will try to bond with other substances, pulling them apart and breaking them down much like a group of water molecules. However, since H+ forms ionic bonds, it is much stronger and more violent than water molecules, which can be very damaging to living tissues. It can rip them apart. pH stands for potential of hydrogen. The P is really an abbreviation for the mathematical operation log 10, a logarithm. pH equals 7 indicates a neutral solution, one in which acids and bases balance one another. Bases are OH-. So if you put together an acid, H+, with a base, OH-, you get H2O, which is nice, neutral water. Solutions with pH 7 are basic, alkaline. Differences in pH represent exponential differences, because of the logarithm, so small changes in pH represent large differences in the amount of acids and bases in the solution. For example, pH 6 means there are 10 times more acids than bases in the solution. pH 5 means there are 100 times more acids than bases in the solution. Slide 13. Today the average pH of the ocean is about 8.1. So, the ocean is a little basic, alkaline, but close to neutral. Fortunately for living things, there are carbon substances dissolved in ocean water which help keep the ocean close to neutral, not too much acid H+ or base OH-, the opposite of acid. When carbon dioxide from the atmosphere enters ocean water, it bonds with water molecules to become carbonic acid. Rain weathers the rocks of the land, breaks them down, and washes the bicarbonate and carbonate that result from breaking down the rocks into the ocean. The pH of the ocean is determined by the relative amounts, the balance, between carbonic acid, bicarbonate, and carbonate in ocean water. If the ocean is too basic, carbonic acid will release acid into the ocean, neutralizing the base, and become bicarbonate. If the ocean is still too basic, bicarbonate will release more acid into the ocean and become carbonate. Similarly, if the ocean is too acidic, carbonate and bicarbonate will absorb acid out of the water, making the ocean more neutral. In other words, these substances, carbonic acid, bicarbonate, and carbonate, release acid when the ocean is too basic and absorb acid when the ocean is too acidic, keeping the ocean close to neutral pH. Remember, the ocean is actually a little basic, on average. We call this process buffering. The fairly neutral pH of the ocean makes it better for ocean life. If ocean water were too acidic or basic, it would begin to dissolve, break down, their bodies. Slide 14. Unfortunately, much of our carbon dioxide pollution from burning fossil fuels, like gasoline or coal, leaks from the atmosphere into the ocean each year, about half of it in the past, now closer to a third or less. Scientists have observed the resulting decrease in ocean pH, and are particularly concerned about organisms that make their shells out of calcium carbonate. As was discussed in the previous paragraph, if the ocean becomes too acidic, carbonate absorbs acid. This removes calcium carbonate from the water that some ocean animals and algae need for making their shells. If the water becomes acidic enough, the calcium carbonate shells of ocean organisms begin to dissolve, the carbonate breaks its bond with the calcium, and bonds with the acid instead. Even if this does not kill the organisms, acidic water makes it harder for them to grow, draining their energy supplies and therefore making it more difficult for them to survive and reproduce. For example, one study has shown that forams, a kind of zooplankton, have calcium carbonate shells almost 40% smaller than those of fossilized foram remains found in ocean sediments. The good news is that by dissolving, the ocean organisms are buffering the ocean, keeping it closer to neutral than the water would otherwise be, which helps other living things in the ocean. I like to say that the animals and algae with calcium carbonate shells are taking one for the team when they dissolve. The concern is that fewer phytoplankton and zooplankton will survive, so there will be less food for animals higher up the food chain including us.